So let me introduce our speaker. Our speaker today is Hershel Safer. Hershel helps organizations improve their operations using advanced mathematical and statistical software, especially from the fields of machine learning and mathematical optimization. Hershel has extensive experience developing quantitative models in various industries, including finance, biopharma, and communications. Hershel has a Ph.D. from MIT in operations research and an undergrad degree from Yale in applied mathematics and economics. And today, Hershel will speak to us about the Gini coefficient, which is often used to measure the quality of models in the realm of credit scoring. The details of how to interpret the measure are often misunderstood. This talk will present the Gini coefficient and show how it is used and explain its significance. Hershel, I'll hand it over to you.
Okay, thanks, Eliza. Let me share my screen. Okay, if this is working right, you see just the slide. Do you see just the slide?
Yes.
Okay, good. So I'm Hershel Safer. Thanks for the introduction, Eliza. I do consulting in advanced mathematical software. I'm located in Israel, but I have worked with clients around the world. And so the intended audience is people with some background or interest in data analysis or credit scoring. There are people on this presentation here who know 10 times as much as I do about all of this. So I hope that some things will be I'll probably go into too much detail for some of you on some of the math and not enough detail for others of you. But if it's not enough detail, then hopefully you'll have something to move, enough to guide you to go learn more. So here's an outline. We'll talk about this fellow Corrado Gini and statistical measures of dispersion. Then we'll talk about I'll give you some background about the credit scoring context and talk about measuring the quality of scorecards and then technical issues. And finally, we'll talk about Gini and problems with using Gini. So this guy's name comes up in a bunch of areas in machine learning. And so, Lisa wrote to ask me if I'd be willing to give a presentation. And so I said yes. And then I had just been wondering recently why his name shows up in so many places and how those different places are related to each other. And so I figured this would be a chance for me to go learn about that and then share it with you. So this fellow Corrado Gini was an Italian statistician around the turn of the previous century, and he created this measure of income inequality in order to compare countries on income inequality. It turned out there was some dispute with Pareto, who many of you may have heard of in Pareto optimality, so in around 1912, he published this, and so it measures how different the cumulative distribution of income is from a uniform income. So if we look at this, do you guys see the cursor? Yeah, okay. So if everybody had the same income, then in every decile here, you would have 10% of the income, of the national income. But of course, real life isn't that way. These are just made up numbers, but suppose that the lowest 10% of incomes came to about 1% total, and then the next 10% came to another 2%, and then the highest 10% of earners earn 25% of the income. Okay, and so we look at the cumulative sums in the last two columns, and so we want to ask how different are these distributions. So here are the last two columns. And so we're going to plot, and the green line here is we're plotting, here's the first 10%, of people, and they have 1% of the income, and then the next 10% have another 2%, so we're up to 3% total, and so on. And then when we add the last 25% for the highest 10% of earners, we have 100%. Whereas the red line is uniform income, that everybody has the same income. So 30% of the people would be 30% of the income at this third point here. Okay, and so that's a uniform income. And so this is also called the Lorentz curve. And so this yellow area in the middle represents somehow the inequality of the income distribution. And if say the high earners had an even greater percentage, so the line would only come up to here, you'd have a greater yellow area. So the bigger the yellow area, the more unequally the income is distributed among the population, among the population in some country. And so we can measure the Gini index of income inequality is the area of this yellow region divided by the area of this triangle, the area under the red line. Okay, so that's the Gini coefficient. And then in the case of when he developed this in 1912, he did this for each country and found, unlike, in contrast to what Pareto was expecting, that wealthier countries had a more uneven distribution of income. Okay, so that's where this all comes from. Okay, that's not what shows up in machine learning, but this is where it comes from, and this is the person. So the place that Gini shows up most often in machine learning is in building decision trees. Okay, so if you read the documentation of more or less any machine learning algorithm that uses decision trees, whether it's just a plain decision tree or a collection of them, such as random forest and gradient boosted decision trees, you see Gini impurity. And that measures, you're building a tree and you want to, you've built it up to a certain point and you want to split some node. Okay, and so it measures the quality of a split. On the next slide, we'll see an example. So Gini impurity is also some kind of measure of dispersion. And it's the probability of incorrectly classifying a new instance if the instances are just randomly distributed according to what's in the data set. So let's take an example. So here, the circles say that they're ordered. There aren't numbers in the circles, say they're ordered from left to right. And this represents values of some variable. And we want to decide where are we going to split this node with these 8 instances to create 2 children. Okay, and what we're going to do, what's typically done when you're using Gini impurity, is you want to maximize the gain. You want to decrease the impurity as much as possible. Okay, so the parent node here, the top line, has a Gini impurity of 1/2, because if the circles are distributed, the colors are distributed according to the 8 that are here, 4 of one and 4 of another, and you randomly assign, you pick some node, some circle, and you randomly assign it a color without knowing its color based on that distribution, then you're going to be right about half the time. Okay, or you're going to be wrong half the time. Okay, so now we have to split, when you're splitting a node into decision tree, you have to choose what value you're going to split at. You're going to split between some pair of circles here. So suppose we split after the 3rd circle. So we end up with one node that's all yellows and one node that has 4 oranges and 1 yellow. Okay, so the Gini impurity of that is 0.2. You can go and calculate it offline. You now know how that's done. If we split after 4 circles, then both children nodes are mixed, and the Gini impurity is 0.38, and so on. And then by the bottom here, when we get to having, again, a pure node, it has only 2 oranges, and the other node has 4 yellows and 2 oranges, the Gini impurity starts to improve again. So it's gone up, and then it's come down. Okay, and so that's the method that's used. That's the criteria that's often used for splitting nodes and decision trees. And actually then afterwards, when you go to measure the importance of variables in your tree-based machine learning algorithm, you look at the total reduction in Gini impurity that resulted from splitting on each feature, and that tells you which features are the most important. Okay, so that's Gini for income inequality and Gini for building trees. Now the rest of the time we're going to talk about credit scoring. Okay, so here's the picture. Some potential borrower, or it could be an individual, it could be a company, goes to some lender to try to get a loan. And that lender might be a bank, it might be some other kind of institution that gives loans. These days, there are a lot of online lenders that are not banks. And the lender has to decide whether or not to give the loan. Okay. And so how does the lender do that? So the lender somehow wants to decide, would this be a good loan to make or a bad loan to make? Okay, and that can have many meanings. It could mean that it's going to be a bad loan if there's a high probability of default, which means that the loan won't get paid back at all or won't get paid back completely. It could just be a high probability of late payment, that the person or the company is going to pay back the loan, but is going to pay later than the contract says that the loan should be paid back. Or it could be fraud. It could be that really it's a home improvement loan, but the person is taking the money to gamble on horse racing or something. Okay, or it could just be somebody pretending to be the person, but it's not really the person whose name the loan is being taken in. So there are many possible meanings for what is bad. Okay, but the lender has some definition of what is bad. Now this is also going to depend on the lender's goals. So it's one thing if you're a commercial bank, if the lender is a commercial bank, and that lender is really focused on getting the loans paid back and paid back on time. And that's true whether it's a personal loan, I'm going to the bank and saying I'd like to borrow $50,000 to remodel my house, or if it's a business loan of some kind. But it's different if it's a credit union, because a credit union has as part of its goals to serve the community, to encourage home ownership. So they may be willing to give a mortgage that a commercial bank would not be willing to give. A credit union might be willing to take more risk because that's part of their goals to encourage building of the community. Okay, they're also different. I use different words here, like I said, high probability of default. Well, how high is high? Okay, so what am I willing to accept 10% chance that the person will default, a 50% chance? I can also have to decide how much is worth classifying as being unpaid. So if I pay off all but $25 of my credit card, is it worthwhile for the credit card company to consider that as unpaid, or is it too small to be concerned about? For a mortgage, maybe the number will be different. Maybe it'll be $200. And so on. And then there's the length of time that is considered late. So maybe I automatically get a 1 week grace period or a 1 month grace period. For a commercial loan, it might be a 3 month grace period before the lender considers this to be late. So there are all sorts of words that I use that the lender also has to decide what are my definitions of that. Now that will differ from one lender to the next. Okay, so what happens if the lender makes a wrong decision? Okay, so there are four possibilities about truth and decisions, and they can be summarized in what's called the confusion matrix. So suppose, now there's this, in machine learning in general, this notational or terminology. So typically, the negative case is the good case, and the positive case is the bad case. Okay, so that seems a little odd, but if you think about, say, medicine, and you go for a test to see if you have, I don't know, you have some particular disease, and the test comes back negative, then you're happy, right? That's the good case, and that's the typical case. If it comes back positive, then you say, oh, I better go see my doctor. That's the bad case. It's the outlier case, the unusual case. So you have to keep in mind when we say negative, we're talking about the usual case, which is usually the good case. Okay, so suppose that negative in this case means the guy's going to pay back the loan. It's not going to default. So, and I predicted that it's going to be negative. So that's called a true negative. Okay, I've said I predicted negative and it turns out to be right. Okay, but sometimes I'm going to say negative. I'm going to say, oh yes, give the guy the loan. It's a good application, but it turns out he's not going to pay it back for whatever reason. He's going to default on part of it. So that's a false negative. I predicted negative, but I was wrong. So that's called a false negative. Likewise, it could be that I said, oh, this guy isn't going to pay back the loan. It's a positive case. It's a bad case. And it turns out he wouldn't have paid it back. So that's a true positive. But sometimes he would have paid it back. Okay, well, of course, I haven't given him the loans. We don't know that for sure. But if I try to do this with historical data. Okay, so that's a false positive. I've said that it's a positive case, and it's not going to get paid back, but it would have gotten paid back. So that's called a false positive. Okay, so these are the four cases. And if you're doing anything having to do with binary classification, that is, you've got a good case and a bad case, and you're trying to classify, this will come up all the time in these terms, true negative, false negative, and so on. And I just want to mention that the false positive rate is the number of false positives. So I'm going to look here at the things that I've called positive, the things that I said, oh, these are bad loans. Okay, these bad applications, don't give the money. The false positive rate is the number of false positives divided by the actual number of negatives, and the true positives divided by the actual number of positives. And it's important that these are columns. These only involve each ratio involves numbers from a single column, because I've calculated the false positive rate only by looking at negatives, only by looking at good loans. And I've calculated the positives only by looking at bad loans. And we'll see later why it's important. It means that they don't affect each other. I don't care what fraction of the population is negative. I've calculated this just based only on negatives. So we'll see later why that's important. Does anybody have any questions at this point? I can't really see all of you because I've got other stuff on the screen here with my notes. So let me know if there are questions. So suppose that the lender makes a mistake. So there are two kinds of mistakes, right? There's false positive and false negative. So what happens in the case of a false positive? Means, what is a false positive? It means I've said that it's positive. I said it's a bad loan. I've rejected it. Okay, so what's the downside? Well, I'm losing the potential income from the loan, and I would get interest from the loan, and perhaps fees if there are late payments and stuff. So it's potential income down the road that I've lost. And of course, I've also lost the customer, because presumably, most of you have had the experience that you call your credit card company to ask a question about one thing, and they say, oh, as long as we have you on the phone, can we interest you in some other product that our company offers, a bank account, some additional kind of credit card, a loan, whatever. So you lose the customer, so you can't then try to sell some other product to the customer. That's if I mistakenly reject. But suppose it's a false negative. I say, oh, this looks like a good loan, but I'm wrong. So I mistakenly grant the loan. Well, the downside is that I lose, the big downside is I lose the money that the customer doesn't pay back. Okay, now this is an out-of-pocket expense. Losing potential income is a sort of theoretical loss down the road, but this is an out-of-pocket expense, and this is money out of my pocket right now. Okay, so there are different costs to the two different kinds of mistakes. Okay, and so I don't mind having some false positives if it means I have fewer false negatives. Okay, because the false negatives are much more expensive. Not to mention that I get an unwanted customer who might be calling me to bother me. Anyhow. Okay, so those are the kinds of mistakes. So how do the lenders work? Okay, so for historical reasons, like from days before we all had computers that we carry around with us all the time, whether it's your laptop or your phone, you actually had something called a scorecard. Okay, it was a physical card, and they would fill it out with the features associated with the loan request. So here we're just calling them X, but it might be the person's income if it's a personal loan, and his expenses, and how often he's defaulted on other loans, and whether he's married, and does he own a house, or does he rent? These days it might be, does he live with his parents? So there are all sorts of features about the person, and of course the size of the loan. And then from that scorecard, I'm going to compute a score with some statistical model, which we're not going to get into any of that today, but there's some statistical model, okay, that computes a credit score based on the information about the person and the information about the loan. And so if the person or the potential borrower has a score that's above some threshold, then I give him the loan. And if it's below the threshold, I don't give him the loan. Okay, and so we make it very easy. I mean, the hard part is in building the statistical model, but once the model is there, you just say, okay, the person has filled out, in the old days, of course, it was on paper and filled out a 20-page application. These days, he's doing it online. And these days, I'm also maybe scraping other information about the applicant from internet sources. But I just put it conceptually into this physical scorecard. Now it's electronic. Compute the score, and just based on that, decide whether or not to give the person a loan. So there are different kinds of credit scores. Okay, so one possibility, just based on what we've talked about till now, is what's the probability that this is a good loan? Okay, that this loan will be paid back or paid back on time, not fraud, whatever it is. And I say, what's the probability that this is a good loan given the application the person has filled out, given the information I have about the person and about the loan? Okay, but there are actually two other measures that are equivalent in the sense that each of these three measures contains all the information needed to compute the other. So I can compute the odds, which is the probability of good divided by the probability of bad. If you've had any kind of statistics course, you've seen this. And then I can also take the log odds, which is the log of this. So you might ask, why bother, right? I've got probability. Why not just leave it at that? Why do I have to go calculate the odds and then the log of the odds? Well, it turns out the log odds has useful properties, which is are not part of the talk today, but the log odds have very useful properties, both in terms of the statistical models that have been used, but maybe less so, but say from 1950 till 2000 or 2010, logistic regression was pretty much always used. And this is related to that, but it also has other properties in terms of separating out what happens in the population from what's special about this person. Okay. So I've got these are common scoring functions. You can think of others. but very often log odds is what's used. So I've got some credit score. And now I've got this scorecard, right? My list of features. I've got a score that I calculate from those features, okay? So now I want to ask, how good is my scorecard? Okay, in other words, how good is the statistical model? What I'm really asking is, how good is the statistical model that I use on my scorecard? Okay, so there are various ways to measure that. And three of the most common ones are, first is discriminatory ability. That is to say, I've got all these potential loans. Say I've got 1,000, right, or 10,000. I just want to rank them in terms of risk. I'm not trying to predict the probability of a bad outcome. I just want to rank them from best to worst. And then somewhere in there, at some point, I'm going to have to decide where my cutoff is. So when a new one comes in, I know if it's above the cutoff or below the cutoff. But it's simply ranking the loans. And we're going to talk more about this as we go on. The next possibility is to actually have calibrated scores that estimate a real probability of a good outcome or a bad outcome. And then the next step beyond that would be to say, okay, I'm not just going to have a probability, but I'm going to decide what's high and what's low. What probability of a bad outcome am I willing to accept? Okay. And so this third measures my ability to make a correct decision. Of course, given my goals as a lender, whether I'm a commercial bank or credit union or a new internet fintech that's making loans. So discriminatory ability is the most qualitative, and then we get to harder numbers, and finally into actual decisions. Okay, so traditionally, and less so in recent years, we'll talk about that at the very end, the traditional way to measure quality was discriminatory ability. That is, say, how well can I separate the goods from the bads? Okay, so suppose that I've got my statistical model that gives me a credit score, and so the blue here, the blue shows the distribution of credit scores for good applicants. And based on historical data, people have actually paid back their loans or paid back their loans on time, whatever criterion I'm using. So this is all made up data, but it'll be the same data set for the whole rest of the talk. So I find that the peak here is at a score of about 50. And then there's some standard deviation. And so the scores go up to about 80 and go down to 2, looks like, okay? I mean, I happen to know that they go down to 2. So there aren't too many scores below 20 for good applicants, but there are some lower scores. Among borrowers, people I actually gave money to who defaulted, say, over the last year, here's the distribution of scores. So the mean here, there's a peak here around 30, and there's another peak around 10. But some of them actually have scores going up to 80. Okay, so a smaller fraction, this is probability distribution. The density is pretty low, but there are even some that have high scores. Okay, so we need to choose a cutoff, right? The whole point is we need to choose some cutoff score, and we say above that cutoff score, say here maybe, I don't know, 35. If it's above the cutoff score, we give them the money. If it's below the cutoff score, we say no. Okay, so say it was 35, then what would happen? We'd be rejecting some that were good, and we'd be giving money to a whole bunch that were bad. So maybe since the bad ones are more expensive, maybe we choose a cutoff around, I don't know, 45. So then we're not giving so many bad loans, but we're losing all these customers that are below 45, and there are a lot of them, of the blue ones. So there's this trade-off, okay? But the whole point of the discriminatory approach is to be able to separate the goods from the bads. And we see that with this statistical model, on the face of it, it looks like it doesn't do such a good job. But we'll see. Maybe it's better than it looks. And it also depends on how risky the lender wants to be. Okay. So one thing to note is that this discriminatory ability depends only on the scorecard. Okay. It doesn't matter what the fraction of goods and bads in the population are. I've calculated the distribution of scores for bad just based on the bad population. I've calculated the distribution of scores for the goods just based on the good population. You can't tell whether there are equal numbers of goods and bads in my made up data set, or if there are a lot more goods or a lot more bads. I mean, as it happens, there are 1,000 goods and 80 bads. Okay, but you have no way to tell that from looking at this picture. The picture is independent of what's called the prevalence of goods and bads. What fraction of the population is one or the other. So if I'm not quite sure what you've covered in this data science class, but if you learn about sensitivity or recall or specificity, if you have any familiarity with medicine, you'd see sensitivity and specificity with regard to medical tests. In this sense, it's just like sensitivity and specificity, because sensitivity is measured only on the negative instances. The sensitivity of a medical test only has to do with the people who are healthy. Specificity of a medical test has only to do with the people who are sick. Okay. In contrast, if you've been doing machine learning, maybe you've run across precision. Precision depends on the test and on how much of the population is good and how much is bad. Okay, but we don't have that here. Okay, each group is measured separately. Okay, also the discriminatory ability is independent of this cutoff score. Okay, this is what it is. Now, when I want to actually have categorical predictions and say, okay, these are the guys I'm giving the money to, I have to choose a cutoff score. But at this point, I don't have to choose one yet. Okay, so this is independent of the cutoff score.
I just want to check, Hershel. I just want to check if we have any questions up to this point.
Okay.
If anybody has questions, just come off mute and ask. Okay.
Okay. So my question is then, how well does this statistical model, how well do these two distributions separate the good from the bad? Okay. So what we're doing is measuring the difference between the distributions of the scores in the good and bad groups. So if you've had any statistics courses, you've already learned about the Kolmogorov-Smirnov statistic, which is just the maximum. If I convert these into cumulative distribution functions, I just take the maximum vertical distance between the two cumulative distribution functions. So you've probably seen that. You probably have not seen Kullback-Leibler divergence, but it's another measure of the difference between the distributions of these scores. And you probably have seen the Wilcox and Mann-Whitney U statistic, which is similar to these, but it's using only the ranks of the values rather than the values themselves. So here we've got the actual scores, but for the Wilcox and Mann-Whitney, we just sort them. We don't actually look at their values. Okay, so I'm not going to give examples of these. Hopefully you've seen the first and the third in class. What we're going to talk about now is what's called the ROC curve. Okay, so it's a visual way to compare the distributions. Okay, and so here, let me just pull my notes up. Okay, so what we're plotting here in the ROC curve is the false positive rate, the true positive rate versus the false positive rate. So what happens? down here, we're setting a threshold. So remember, above a certain threshold, we give the loan. Below the threshold, we don't give the loan. Okay, so if we set the threshold to 0, we're down here in the lower left corner. That's like here in the lower left corner. We're giving everybody who wants a loan gets a loan. Nothing, and nobody's rejected. So there are no true positives, but there are no positives, right? We haven't labeled anybody as being positive. No true ones, no false ones. So we're down here, false positive rate is 0 and true positive rate is 0. But now we say, oh, we can't just give loans to everybody, right? We've got to be at least a little bit discriminating. So we're going to increase our threshold. We're going to start increasing our threshold over here, maybe to 5. So what happens? Well, when we increase it to 5, we're going to start rejecting some, but almost everybody we reject is going to be in the red. They're going to be positives. Okay, so the true positive rate starts going up without any real motion on the x-axis. Okay, because there are very few positive and very few negatives down here. So we're not going to have false positives. But once we start getting here, we get to about 20, okay, a threshold of 20. Now all of a sudden we actually start to see some false positives, some potential borrowers who would have been good borrowers, but we're rejecting them when the threshold gets up to 20. Okay, so now we start to be around here. And as we keep going, once we get, say, to 40, we're rejecting most of what we're rejecting is bad applicants. We're rejecting a fair number of good applicants. We're now around here. And as we keep increasing our threshold, once this threshold hits 80, we're rejecting everybody. Okay, so all the true positives have been rejected, but also all the false positives have been rejected. So we're up here at 1, 1. Okay, so we get this curve, and this is what's called the rock curve. Okay, when the threshold is very tight. Okay, and so similarly to the notion of income inequality, ideally, well, I think actually I have this on the next slide. Let's see. Yeah. Can I get to the next slide? There we go. Let me just mention also this blue diagonal line. This represents random decisions about accepting and rejecting. Okay, so somebody applies, I just flip a coin. Okay, and so I'm going to have equal fractions of of good applicants and bad applicants being rejected. Okay, so ideally, in an ideal world, what would happen? I'd have, at the beginning, I'd just reject all the bad applicants, and then I'd accept all the good applicants. Okay, so my line, this red line, would just go from 0, 0 to 0, 1, and then to 1, 1. That would be the ideal. So, of course, that never happens in real life, but the closer the red line gets to the ideal, the better we think it is. Okay, so this area in here, when we'll talk about this, okay, we'll come back to that. Okay, so suppose I have 2 statistical models, 2 different scorecards, and how do I compare them? Okay, so if one of them is just inside here, it's clearly dominated by the outer one, then that's easy. It's a little harder if they cross. So how am I going to measure how good this rock curve is? Okay, well, the way I'm going to measure it is by looking at the area under the curve. Okay, so this whole box has area of 1, right? 1 on each side. And the area under the curve is what I'm including in my rock curve. So this has area under the curve of 0.847. Okay, so in real life, that's actually quite good. And if I had some other curve, then I might look at it, the area under that curve, and I prefer the one generally, though not always, that has a higher area under the curve. So I'm looking at the area under the curve. Now, here I've drawn it so that this red curve is above the blue curve. You could, in principle, have a curve that's underneath the blue curve. Well, but in that case, you say, oh, this is so bad, I just need to switch which ones I accept and which ones I reject, and then it would be above. Okay, so in practice, the area under the curve is greater than a half. You've got half of the box underneath the blue line, and so we've got some extra area. Okay, and so I have area under the curve values from 0.5 to 1. Okay, so 0.5 to 1 is sort of inconvenient. Okay, we're used to thinking in terms of like probabilities between 0 and 1 or 0% to 100%. A half to 1, it's just less natural. What if we wanted to just scale it to be between 0 and 1? Well, what if we, in other words, what if we just said, okay, what about this part, the orange part here between the red line and the blue line, divided by this area above the blue line? Okay, that'll be a number between 0 and 1. Okay, and this is the Gini coefficient as used for discriminating between distributions and is used in credit risk. Okay, so the Gini is 2 times the area under the curve minus 1. You can figure that out just geometrically here. And so this is about 70% or 69% of the area above the blue line. Okay, so this is what we've been aiming for. So it's another measure of statistical dispersion, similar to the other Ginis we've seen. Okay, so it's the raw curve, as I mentioned, is independent of the good and bad prevalence in the population. It's just a property of the statistical model that's underlying the scorecard. And the same is true of the area under the curve and the Gini coefficient. They just are properties of the scorecard. Okay. Now, looking at this picture, you might say, oh, this is just like the picture from the beginning, right? It's just like this picture just flipped. Okay. You might say, oh, it's just the same thing as this measure of dispersion of income inequality. In fact, it's reminiscent, and the 2 curves share some similar properties, but they're different. And not only they're different, you can't even get from one to the other in a simple manner. They're related, they have properties in common, but they are not directly related. But they all share the name of this fellow Gini as measures of statistical dispersion based basically on the ranks of the numbers involved. Okay. Questions so far? So I said, well, then good. Okay, now we know the Gini curve. We know how banks might use this. So that's wonderful. But in fact, there are issues with the Gini coefficient. It's not the end of the story. And there are substantive issues. So first of all, this is measured over the entire range of thresholds. Okay, remember we had to choose some threshold for picking where we're going to give the loan. Okay, so it's measured, Gini is measured over this entire range from 2 to 80. But in fact, we're not going to choose a threshold here at 75. And we're not going to choose a threshold here at 20. The threshold is going to be, I don't know, somewhere between, say, 30 and 60, 35 and 55, something like that. So we're measuring our ability to discriminate over the whole range. But in fact, we're only going to be looking at a subset of that range. Okay, so I don't actually care that it discriminates very well down at the bottom. And I don't care that it discriminates very well at the top. I want to know how well does it discriminate right in here. Okay, and actually, as you go further in data science, especially if you go into machine learning and People use area under the curve all the time. ROC curve is the standard way of comparing classifiers, and they look at area under the curve. That's how they measure it. Well, it's not always appropriate. It's not always sensible. Okay, here, it's just not sensible to be looking at the entire range. You want to be looking at actually where your threshold is going to be. Okay, so keep that in mind next time someone tries to sell you something based on area under the curve. Second, well, I guess most of the people here were fairly young in 2008 when banks went out of business because of the subprime mortgage crisis. But there's been a lot of focus in the last decade on how risky are banks' loan portfolios. Okay, well, if you remember, we talked about here, discriminatory, we're focusing with Gini on discriminatory ability. The Basel Accord is they're called the Basel Accord because the Bank for International Settlements is in Basel, and that's where the discussions were, and continue to be. We're up to, I think, the 5th Basel Accord now. The Basel Accord require actual estimates of risk, okay? Numbers, not just, yeah, we can rank them and figure it out. We need actual numbers of risk. So if, say, up to the year 2008, maybe Gini coefficient was perhaps sufficient or considered okay, less so in the last decade, okay, or last 13 years. With banks, large banks failing or large financial institutions failing, it's really, there's much more at every country with banks, which is every country and also at the international level. We want to know actual real risk estimates. Finally, we've talked about 2 categories, just give the loan, don't give the loan. But there are other situations where you might have multiple categories. It's still well defined, but it doesn't, the value is sensitive to the number of categories. If you have a lot of categories, then it doesn't work as well. And so there are also situations where it just doesn't work. Even if Gini coefficient is appropriate, it just might not work so well when there are many categories. Okay. And then the last there, I just want to mention a few sources. I mean, over the years, I've read many things, but I think these are the most relevant to this. Christine Bolton, I don't remember her married name, but her master's thesis at the University of Pretoria in 2009 covers a lot of interesting, if you're interested in this area, it covers a lot of interesting background. You can find that online. David Hand from the University of Edinburgh, I think, has written a lot on machine learning and credit risk. And he talks about some of the problems with area under the curve, which is the same as problems with Gini. Rizek and Rizak have it's a nice survey paper. There's a fellow here in Israel, Idan Schatz, who wrote this, has a blog post about this. And then Lynn Thomas, who's written a number of books in this area. There's one called Consumer Credit Models, which also has a lot of useful background in this area. So last chance for questions. If people have questions.
Thank you, Hershel. This was very interesting. Anybody has questions, please come off mute. Questions either about credit models, anything in finance, Gini, machine learning. You have an expert here, take advantage. Hershel's done a lot of modeling and also a lot of training. So any questions, please.
Yeah, it's a question. I was just confused. How do you optimize for the unequal values of the true or the false positives and the false negatives? because AUC, it assumes an equal value of false positives and false negatives, but you're saying that different types of defaults and missing out on someone who's going to give a loan to, and defaulting are very different values.
Yeah, so that goes to choosing the threshold. Okay, so the AUC is the AUC over all the thresholds, and that goes, well, your question is basically goes to picking the threshold. Okay, so given if I pick a particular threshold, then I can calculate my expected gains and expected losses. I have some idea of what my expected my gain is from giving a loan, and my expected loss if the loan turns out to be a bad loan. And so you can calculate an expected value. And in fact, what's important there is not the actual cost and gain, the cost of losing a loan and the gain of giving the loan, but there's the ratio between those values. And which means you can have a lot more certainty about the ratio than about the actual numbers. You can then calculate an expected value for any threshold and pick a threshold that makes sense for your company.
Thank you very much.
That's it. That's independent of the AUC, essentially.
Other questions?
Yeah, sorry for the late response. I was just trying to get to a place where I could ask this question. So we're, I don't know if you had heard from before, but our particular team in our program is working currently on, like part of our project is using a predictive model to try and determine the like how a particular stock will perform over the next however long, let's just say the next quarter, for example. What do you think are the most important variables in this model, in these types of models, to really take into account in order to really, because like a lot of this stuff is that it'll just follow us like the same pattern over and over again until it doesn't. Like that's like how a stock works, that it'll follow a pattern until it doesn't. So what do you think like are good indicators of like a good, I wouldn't say an accurate, because like you obviously can't predict these like 100%, but what you've seen so far?
So there are a lot of it depends with regard to that. Okay, so first of all, if you're, it depends, are you trying to say, I want to identify the next Apple, right? Or, I want to identify the next WeWork, or well, maybe WeWork is a good example. But I want to identify the next Apple, it's just going to at some point explode. That's one kind of prediction. Or are you trying to do what's called statistical arbitrage, where you say, look, I don't want to identify the next Apple, but I want to, trade across all of the New York, stocks on the New York Stock Exchange and make small amounts of money each day that eventually add up to a lot of money. Okay, so there you have large numbers, and law of large numbers can be your friend. And it's a different, much more data, and it's a much different picture. So I don't know if you're trying to do, say, I want to pick the next blockbuster, or I want to just, do well trading over the, all of New York Stock Exchange.
I would say that it's the latter.
Okay, so I want to do well, say, looking at, all of the New York Stock Exchange or all of NASDAQ. So then the next question is, how much time and effort do I want to invest in this? Okay, because I could say, okay, I've got this huge team full of experts, and I want to create a international macroeconomic model, because of course these stocks aren't only traded in New York, they're traded around the world. Okay, and they're traded around the world. If the day starts in Tokyo and Hong Kong, and then as the day gets to the middle of the day, then the markets open in Germany and Berlin and Paris, or Frankfurt and Paris, and then eventually they open in New York. We're trading around the world. Okay, so do I want some huge international macroeconomic model, or do I want something very simple because I'm working on my own, or I'm a small team, or I don't have access to a lot of data? And so then, if you're doing some big fancy model, then you need, interest rates and currency exchange rates and changes in currency exchange rates and stuff like that. And trading volumes and prices and things like that. On the other hand, if you want to do something simple, let me see if I can find a reference for you here as an example of a paper that said, look, I'm not going to get into lots and lots of data. I'm just going to look for situations that may have been similar in the past. Let me just, I know I have this paper somewhere, right? Here we go. Here we go. And Zoom, I'm just going to paste this into chat. Let's see how it comes out. Yeah. Okay. So, take a look at this paper where, basically they say, okay, I can't spend a lot of time modeling 500 variables. I'm going to do something different. I'm going to look for days in the past that look like today. And it's nice. It's also nice in the sense that they it's sort of a combination of various techniques of machine learning. It uses ensembles. It also uses nonlinear optimization. It combines a lot of different statistical and mathematical techniques to use very simple data to get a very powerful result. So that's another kind of it depends. How big is your team and what data do you have access to?
Okay.
And so this, it's not the easiest paper to read, but maybe between all of you can figure it out. But it's a nice example of getting a good result for statistical arbitrage using simple data.